friends, welcome back. Now let's see the problems associated with the page table when the size of the process is too big. So we have to use some alternative way to solve this problem, and that's what we call a inverted page table. So what problem we do have is in our normal paging, every process has its own page table which maps the virtual pages to the physical pages. So that is every process in our system will have one page table, and that maps the virtual pages of the process to the physical frame where these pages are occupying. So that's a diagram which shows that the page table is associated with every process, and then we do have the page number and then displacement we get from the CPU pertaining to that page table of that process we are talking about. So this page table is available one per process. So currently a CPU is working with a particular process, therefore it is using a particular page table. And when we want to extract something from the memory or use some part of the memory, then we do give the two components, one the page number, that's a virtual page number, and then the displacement, that means inside that page at what location we are trying to read or write. So that's a P and D are given, and this P goes into our page table, and that says which frame this particular page is available in the main memory or the physical memory. So physically where exactly this is located, this virtual page is exactly located in which frame. So that is referenced here, and that reference is taken, the F value is taken, and then the displacement is used, and both together will pinpoint the exact location in the main memory where exactly we are to operate. Yeah, that's a wonderful idea about paging and using virtual pages. So with the limited frames available, we are now able to use unlimited number of pages in the process. So that is possible through virtual paging, and that's a wonderful idea, but it does not come freely. It will come with some cost, and that problem is when the virtual address space is large, then the page tables will be very huge, and will be definitely going to consume a lot of memory. So when the page addresses are large, like 64-bit paging and all that, then the page table becomes very huge, and we do require one page table for every process. Therefore, if we are having n processes, then we are going to have n page tables, and that itself is going to occupy a lot of space. So just making a sense that where our pages are located and all, to just create a contents table or the index table, we are using a lot of memory. So it's something like usual if you just consider any book and all that. So book is of some hundreds of pages, 500s of pages and all that. And if you just look back at the index at the end of the book, few pages are used for indexing. Yeah, that's logical that if you have few pages used for indexing where the page size, where the book size is of hundreds of pages, it's logical. But what if half of the book is used only to index where the contents are, which page the contents are located and all that? If you are trying to use half of the book for your contents or indexing, then definitely it's just a wastage of space. So we don't get sufficient space to write our text. Half of the book we have wasted only for referencing where the text is available and all that. So that was a analogy I can give when we are talking about indexing and all that. So anything you are searching for, just get to the index, and in the index it is listed in alphabetical order. Search for the keyword you are looking for, and it shows in which page that details of that particular keyword are. So just go to that page and then you can read in detail about that keyword and all that. So that's the logic. The same way we are trying to do with this page table. So if whichever page we want to refer, we don't know where exactly it is there situated in the main memory. So we do use page table for searching our page in the main memory. But the problem we are now facing is the size of the page table is going to be very large, then it's definitely becoming a problem. So what is the solution? The solution is the inverted page table. Instead of maintaining one page table for every process, and where you are mapping the page of a process to the physical frame, instead of doing that way, if we can reverse it, that means just we say we have limited number of physical frames. So for every physical frame, if we can say in that frame which page table of which process is located, so that could be easy way, so that can save a lot of our space, and that's the logic of inverted page table. So this inverted page table now has one entry per physical frame, not per physical or per virtual page. We are having one entry per physical frame. So we have fixed number of physical frames, therefore we will have a fixed size, and instead of working with one table per process, we are working on a global level. So here each entry tells which process owns this particular frame. So here we are writing an entry into the frame of the main memory, and this entry tells which process is being used by this frame is used by which process, and what virtual page is used in this particular frame. So we are talking about at every frame we write the reverse way, that which process IDs, which page is stored in this particular frame. So instead of having multiple page tables, that is one per process, now operating system maintains one single global table indexed by the frame number instead of indexing by the PID page number. We index by the frame number. And how it is done? So the process generates a virtual address, and the operating system extracts the page number and the process ID. And this inverted process table is searched to find which frame holds that PID page pair. So for every frame we have an index which says which PID, which page is stored in that particular frame. We just search that, and if we found the physical address is generated. Otherwise we just say that such page does not exist on the physical memory, so we have a page fault. Therefore we need to clear one of the frames on the main memory and get that new page onto the main memory. So we need to get a new page from the disk to the main memory. For that, some other page has to be removed, and this searching can be slow because whole memory has to be searched. First location, which PID, which table, which page. Second location, which PID, which page, and that way for every location we keep searching till we get a pair of our PID and our page number pair. Till we get that, we just keep doing, or we may reach end of that and still we don't get, then page fault is declared. So it's going to be very slow. So usually it is combined with hash table for faster lookups. So the logic here is, so the now CPU will give us the PID, then page number, and inside that page displacement. So this PID and the page number are searched in the page table and says that PID page number is located in which index of the main memory. So it just provides us the index, and that index along with the displacement will define the exact physical location of the main memory where we are trying to write or read. So that's about the inverted page table. So that's it for now. Thank you.